So welcome back, everybody. This is chapter 15, which is all about inference for regression. New type of inference. And I've drawn here kind of the big tree diagram of all the different kinds of inference we've learned really since we started doing inference way back in chapter 10. You'll notice right down here I added in inference hypothesis test for many proportions, which is what we learned last chapter with chi-squared. Well, today we're going to learn our last type of inference that's on the AP exam, which is inference for linear regression. Remember way back in chapter 3 we did the least squared regression line, the lsrl. Well, now we're going to do confidence intervals and hypothesis tests for the slope of the linear regression line. And so let's look at some examples. It's going to kind of feel like a little bit of review at the beginning because we probably haven't thought about lsrl since way back in chapter 3. So one of the things we learned way back in chapter 3 was the idea of computer output, which kind of looks something like this. And at the time we learned how to kind of pull out various different numbers in this computer output to figure out the equation of the least squared regression line. So this particular example involves the idea of thinking about heart disease, I think a number of deaths per 1,000 or 10,000 people or something like that, that's the y variable, or the response variable. The independent variable, or the explanatory variable, is the amount of wine consumed per capita, I think in liters per year or something like that. So the idea being that the more wine you consume, the less heart disease there is, which is in the country, which is there's some data that supports that. At the time, we looked at there's lots of numbers in this computer output, but the really only ones we care about are only 4 of them. These two numbers right here are the y-intercept and slope of the least squared regression line. The constant one's the y-intercept. The one that's multiplied by y is the slope. We also talked about this number right here being r squared, which in this case is 0.71. And then we talked about this number right here being the standard deviation of the residuals. For right now, if you just know those 4 numbers, you're in good shape. We'll learn a few more in a few slides. But so if the question just is, what is the equation of the least squared regression line, which remember we always write that as y hat equals a plus bx, where a is the y-intercept and b is the slope, well then here we just look at these two numbers right here. So the equation of the least squared regression line, usually we write x and y in terms of words, so disease hat is 260.603, hey look, that's the y-intercept, minus 22.9994, hey look, that's the slope, times 1. So make sure you're able to do this. Make sure you're able to pull out these two numbers and give the equation of the least squared regression line. If you cared what the r value is, remember that's the correlation coefficient, well r squared is 0.71, so that if you square root that, you get negative 0.84. The negative comes from the fact that you know that if the slope is negative, that means the line is going downhill in general, so the correlation coefficient has to be negative. So if you just square rooted this, you would get positive 0.84, and you have to think, oh yeah, it's going to have to be negative because the correlation coefficient and the slope have to have the same sign. Okay, so that's great, but what does that all have to do with the idea of inference? You know, that everything I just talked about in the previous slide was just review. Remember, inference is the idea of using a statistic to estimate an unknown parameter. That's what we've been doing really since back in chapter 10. Well, here's the key thing. This number right here, the slope, that is a statistic, because how would you calculate the slope? You would calculate it from a sample of smaller data. Imagine you had a scatter plot with maybe only like 19 points. The slope can be calculated from just those 19 points. Okay? That's different than the slope of every single country or every single person in the entire world for the population. This number is a statistic. It's not a parameter. So if it's a statistic, we might think, well, what is the actual unknown parameter? And we can do inference on that. This number is calculated just from the 19 points in the scatter plot. So remember, we call this number b. b is the statistic version of the slope. In keeping our tradition of using Greek letters for the parameters, things like mu or sigma, we're going to call capital B beta is the slope in terms of as a parameter. So that would be the slope of the entire population, which would be every country or every person in the world. Okay? So b, lowercase b, is the statistic. That's the slope of the sample, capital B beta in Greek. is the slope of the entire population. So if we can kind of relate these statistic and parameter things, we can now talk about confidence intervals and hypothesis tests relating to the slope. Our general formula for all confidence intervals is statistic plus or minus critical value times standard error. Our statistic is B. I'm here to tell you today one new bit of information is that the critical value is T star. It does follow a T interval instead of a Z interval or something else like that. And then standard error, for right now, we're just going to say standard error of B. And we'll kind of worry about the formula for that in a second. There is going to be a formula for it, but actually we're not going to worry about it too much. For hypothesis test, again, our general formula is test equals statistic minus parameter over standard error. Test is going to be a T-score. Statistic is B. Parameter is beta. And then again, we're going to kind of punt on the question of what the standard error is and just say, oh, it's the standard error B. These are two pictures from your book that I think might kind of illustrate that idea. In this case, we've got the idea we've got 3 points, and they each follow a normal distribution. So here's 1 point, here's 2 points, here's 3 points. And it's showing the idea that as the points might vary, the slope of the line might change. It's kind of all they're talking about here. It gives you some indication that depending on what points you pick, the slope of your lsrl will be different. And since there's some variance in the points, there's some variance in the slope of the line. Here's the formula I told you before for confidence intervals, B plus or minus T star, standard error B. This is actually the formula for the standard error of B. But it turns out we're actually not going to use this formula at all, if ever, because this number is actually shown in the computer output. So rather than actually just using this formula, we can just look at the computer output in a second, and I'll show you how to do this, and say, hey, there it is. The only other new bit of information here is, notice right here it says T star is the critical value for n minus 2. For this particular new type of inference, the degrees of freedom is n minus 2. When you're talking about everything else we've done before, it's n minus 1. But when you're talking about regression, it's n minus 2. That's a little bit weird. This is another computer output, just another example. I want to just show you how to find the standard error of B. This particular example is a little bit different than the wine and heart disease one. This is talking about how you can predict the IQ of a baby by the number of times it cries. I think it's in an hour. And the idea, the philosophy is that babies cry because they're getting so much sensory input they don't understand, and so smarter babies, their minds are kind of processing this data input that they can't understand, so the only way they can deal with it is they cry. So babies whose minds are thinking more actively cry more. That's the theory anyways. We'll kind of see whether that's true or not. And so what I wanted to show you in this particular one, again, what are the numbers you care about? Well, there's actually not that many of them. Okay, these two numbers are the slope and the y-intercept. The first one's the y-intercept, the bottom one is the slope of crying. In fact, here it actually shows you, kind of matches that up. This number right here is the standard deviation of the residuals. This number is r squared, in this case 0.207. The new information in this particular one is this number right here, okay, 0.487. This is the standard error of beta. So that whole formula I showed you in the previous, sorry, standard error of B, excuse me. That whole formula I showed you on the previous slide, forget that number. If you wanted the standard error of B, just look at the computer output, and it's the number right next to the slope, right? So if this is the slope, look right over, oh, it's a terrible arrow, but if this is the slope, look right to the right of it, and that'll be the standard deviation or standard error. See, it's always under a column that's usually labeled either standard deviation or standard error. So now let's just, using this computer output, say, well, what if the question said give a 95% confidence interval for, oh gee, what's going on with that? That's weird. What if it said give a 95% confidence interval for beta? Well, again, here's our formula for a confidence interval, B plus or minus T star times the standard error of B. B, hey, look, just look up here in the computer output. There it is. It's 1.4928, so that's what I wrote here. I'll come back to T star in a second, but standard error of B, look how easy it is. Look in the computer output. There it is right there. It's 0.4870. And then all you have to do next is find T star, and here it is right here. I got this number by doing inverse T of 0.975, comma, In this case, there were 20 babies, so I'm going to say it's going to be 18. Remember, degrees of freedom is n minus 2. Turns out that's 2.101. So in this kind of, you're not going to the calculator or doing anything else. Really, all you have to do for these kind of inference problems is look at the computer output. There's the one number you care about, there's the other number you care about, and then just put them in the formula, and you can actually just do it by hand. And then your paragraph would be, I'm 95% confident that the actual slope of the lsrl, which would be the increase in IQ score, the increase in IQ score per cry, is between 0.47 and 2.52, and that would be like points over crying. It would be the kind of units of the slope, right? So again, it's the inference toolbox, sort of, but actually we do it with computer output, and we just pull out the numbers we need. Well, what if you want to do a hypothesis test? And the question you would think about here is there evidence that crying and IQ are associated or correlated or related in some way? Before we do that, I want you to just kind of think about one thing. What if this was not true? What if what if crying and IQ had nothing to do with each other? Well, in that case, the scatter plot would just look like a bunch of random points all over the place. Would it just if there's no association or they're not related in some way, a scatter plot would just be a bunch of just points all over the place, right? Maybe something like this, right? I don't know how fun it is to draw points. And if you had to fit a least squared regression line through that, the slope would be 0. So if the actual slope is 0, that's another way of saying there's no relationship between x and y. So that's why when you think about, for these problems when you do a hypothesis test, your null hypothesis is beta equals 0, which in English would mean there's no association. Our alternative hypothesis is beta does not equal 0, meaning there is some association. This is, by the way, as kind of a reason why you could actually, at a little tangent, you could do inference on the y-intercept, but it turns out that's almost never done because what would that even mean? It turns out doing inference on the slope is more interesting because it tells you whether there is or is not an association. We don't have any we can't really attach any meaning to the y-intercept like we can to the slope. So every time I've seen a hypothesis test for slope, these have been your ho and your hi. It's beta equals 0 and beta does not equal 0. Usually we just don't worry about the conditions here. It is in your book in some great detail, and if you really want to know what the conditions for inference for regression are, it's there. There's about 4 or 5 of them, unfortunately. It usually doesn't come up on the AP exam, so I'm going to skip it right now and just kind of get to step 3 of the calculations. But you might want to just flip in your book and look at what the conditions are. So hey, look, here's our formula once you get to step 3. The t-score equals b minus beta over the standard error of beta. B is this number right here, 1.4929. Beta, we think, is 0, so I'll write minus 0 here. Standard error of b is this number right here. And it turns out I get a t-score of 3.07. You know what's really neat about that t-score is actually you don't even have to do it by hand because look, this is the t-score column, and there's that number 3.07. If you had to get the p-value, hey look, the next column is the p-value, and there it is. There's the p-value of 0.004. So it turns out now we actually know if you look in the computer output, this is the x variable, this is the value of b, this is the standard error of b, this is the t-score if you were to do a hypothesis test, and this is the p-value if you were to do a hypothesis test. So actually, this bottom row now, we actually know all 4 of the numbers. Again, the top row, we usually don't talk about these numbers up here because usually we don't do inference on the y-intercept, but if you did, that's what they would mean. And then we just write our last paragraph. It means exactly the same thing as it has meant all along. There's about a 0.4% chance of getting the data meaning these particular points or the particular babies we looked at, by random chance if beta actually equals 0, which in English would mean there's no association between crying and IQ. Since this is unlikely, we'll reject the null hypothesis, and there is evidence, in this case, that there is some association or some relationship or some correlation between crying and IQ, which basically means that beta doesn't equal 0. And that's really all you have to know about Chapter 15. Our book goes into some more detail, but that's really all you really have to know to answer any questions on the AP exam about inference for regression. Just make sure you can look at the computer output and pull out the numbers you need.